Okay, so I'm redoing my electrostatics video because it was kind of mid. But yeah, so I'm going to explain the basics of this unit first, and then I'll go into the math of it, because if you don't understand like the logic or how like it like works, it's not going to make sense when you add math to it. So to understand this unit, you have to understand how an atom is put together. So this is a carbon atom. We have the protons, which are the green ones, and the neutrons, which are the blue ones. In the middle here, it doesn't really matter that this is carbon because it's like chemistry stuff. But what's important is that the electron's on the outside, right? And so they're in these little thingamabobs, and they just like bounce around and stuff. So this helps because you know, when it's just there, it kind of like just hits whatever, you know what I mean? So that's why when stuff has like static electrical charge, that's a word that I probably didn't make up. The electrons are moving, not the protons, because the electrons are freely just floating around and stuff, so they just like move easier, you know what I mean? It'd be really hard to break this up because of like gravity and stuff, and like kablooey would happen. And so this helps with like understanding lightning. So if we have, so like ice is less dense than water, so it goes to the top, and the water is at the bottom, and then we have our negative charges and our positive charges, and those attract. So we have the lightning go up, and then we have the lightning also come down, and it goes psh, psh, psh. That's lightning for you. Is this gonna be on our final? I don't know, but we should review everything, so that's what we're doing. And so this, if there's diagrams, they'll be drawn like, probably be drawn like this, where a positive field is giving out the stuff, and negative fields are taking it in. Think like a battery, right? So like the charge comes out of the top of the battery because it's like the positive, right? And it goes back into the battery at the negative because like circuits and stuff. So it comes out this way and goes back this way. It's the same with like the fields. So, you know, science, like, they made the diagrams based on, like, you know, so that's what they look like. Oh my god, time for Coulomb's law. So it looks confusing, and I thought it was confusing up until 2 minutes ago. But for Coulomb's law, am I saying this right now? Don't know. So it's pretty much just saying force is equal to something E. I don't know. It's a constant. That's
9 times 10 to the 9 times n plus n squared over c squared.
I don't really care what that means, though, because it's not really important. So what's most important is this funny little thing up here with like the Q1 times Q2 over R squared, because this is just like common sense put on paper, okay? So forget the formula, okay? I have magnets, okay? So see how they're stuck together? That's because Coulomb's law has them at a negative force, okay? Because, okay, I'm bringing it back. So each of these is the force, right? And so if this one is positive and this one's negative, so you know when you multiply numbers, when you have two positives, it's a positive. When you have two negatives, it's a negative. Or not two negatives. Two negatives is a positive, and one negative, one positive, it's a negative. Same thing applies here, okay? So the Q should represent your objects and their charge. And so when you multiply it out, if it's a positive number, so if both of them are positive or both of them are negative, you're gonna get a positive for your F right here. And when forces are positive, they go away from each other, okay? But when they're negative, they go towards each other. Wow, that's great. So if your F is positive, they're going away from each other, and if your F is negative, they are going towards each other. And that's great, because magnets be doing that, right? So the force of this would be negative, because they're touching, and they went together. But if I have to flip one of these around, they don't. These are really weak magnets. I'm so sorry. They don't go the fuck? These magnets are... Imagine they're pushing away from me. I don't know where I got these magnets from. Imagine they're pushing away from each other. Okay? And don't go by the battery. That explains Coulomb's law. The basics of it, okay? But when we have, like, word problems and stuff, you have to actually, like, multiply this stuff out. But it's not hard, okay? So that's the basics. And now look at how much more approachable that equation looks because I had magnets. And it's like 2 in the morning and I'm like sleep deprived. But those magnets are broken. Like they connect on both sides. But point is, hopefully this helps. And I gotta do the math now. Bruh. I forgot to explain the distance stuff. So the further away the objects, the less powerful the charge. So let's get my broken magnets and we're gonna pretend like they work. So, the force between these right now isn't... I'm literally going to use something else because, what the actual hell? These two markers, okay? Let's pretend they're magnets, okay? So, if they were this far apart, their charge or their force between the two would be less compared to if they were this close. So that's what the r squared is. And so if you were to double the force, or not double the force, double the distance, you would have 2r squared, which would make you divide this force out by more, meaning that there is less force between them. You know what I mean? Because if they were like 1, they'd be like something, they'd be like touched, you know what I mean? But the bigger the number on the bottom, the more space there is, so the less force, because the number be smaller for force, you know what I mean? So, yeah. Less force, more force. Don't listen to me.